Hello, and welcome back to Android App Reverse Engineering, which was supposed to be live, but as I was trying to get everything ready for this morning's scheduled live stream, I realized my internet was not ready to support a quality stream. So hopefully y'all understand that streaming's not my main gig. I'm just trying to share this information. So hopefully a recording that is better quality gives you a much better experience than if I had tried to get it out as a live this morning. But there was buffering and you couldn't really see with fidelity what my screen is. So here we are, and we're doing the best we can. So as I said before, this is part two. So the prerequisites for taking part of this before you get further into it is first, you'll need the virtual machine that we used in part one, but this is downloaded from maddystone.github.io/androidappre, which is the same place you can find all of the materials and information I present in this recording. In case you prefer to read about the information rather than listening to it in a video, it's all there. Also, you can find the part one live stream recording on YouTube on this channel. So if you have not seen that yet or worked through the previous exercise or sections in the workshop on GitHub, then I'd really suggest doing that because this builds on top of some of those topics. Lastly, part two gets into the native code reversing, which is my personal favorite part of reversing Android apps. But that means there is assumed familiarity with x86 or ARM assembly. So this course will not teach you about those two assembly architectures or instruction set architectures or, an intro to binary reversing. So that would be a starting point before jumping into this material. For ARM, which is what most Android phones are running, I highly recommend the information at Azaria Labs, her tutorials for introduction to the ARM assembly language. So let's get into it. As I said, this in part two is going to be all about reversing Android native code within applications. And so the first thing we need to understand about how native code, meaning usually C or C++, compiled down to whatever architecture the phone uses or the CPU it's running on, that requires us to have an understanding of the Java native interface. So what is the Java native interface? It's what allows app developers to define Java native methods that run in other languages, such as C++ or C++. Because you can think of there's a lot of cases where Java is not the best language to code. So think of things such as intensive math computations or graphics, where you just have such a high fidelity or high performance needs or things like that, that Java just is not as an interpretive language running within a virtual machine. It doesn't give the same output performance, etc. So you want to write it in C or C++ and compile it down. So the Java native interface allows that. And in Android, there's a specialized thing within the Java native interface or on top of called the Native Development Kit, otherwise known as the NDK. And it's the tool set that permits developers of Android apps to write the C or C++ code. And it basically builds this bridge from the Java or Kotlin code that an app really needs to be able to run, and how do you bridge and call into native libraries. And so when we're talking about the native code format within Android applications, what we really mean is it's a shared object library in the ELF file format. So if you've done any work on Linux, that's going to sound extremely familiar, and it's those same file types. They're just now included in our application or APK. So here are some important resources. First, the JNI spec from Oracle. I often have this open, reminding me about, some of the different tips and information. JNI functions I'm always using because it's the APIs that are made available to your native code that allows it to interact with Java constructs, basically. And we'll get into that a little more for the second exercise of today. Next, the Android-specific ones. I really suggest reading the JNI tips that Android provides to app developers because, as I always say, it's much easier to understand how to reverse something when you know how you would build it. And so this is what Android provides to developers. So if you can understand the developer's mindset, how they're supposed to build something, it can really help you in reversing it. And the same is for getting started with NDK. So those are my suggestions. Definitely take a look and read over those because I think they provide great information. And then the JNI functions is something that I suggest just having up while you're working through reverse engineering because it helps you understand the APIs you're running into. So what's our target of analysis? In part one, we talked a lot about APKs, and we really focused all of our reverse engineering on the Java bytecode that is within the classes.dex files, or the Dalvik executables. And here, we're now changing the target of our analysis. Instead of all the code that's in classes.dex, we're focusing our analysis on the compiled code, which is in the SO file, or a native library within the APK. And remember, APKs are just zip files or zip archives, so we can still extract these SO or native code libraries and then analyze them. So how does a Java application, or Kotlin, I'm just going to use Java term as I did in part one, start executing and call into functions that are in a .so or Android native library? Well, the first thing they have to do is they have to load that native library into memory so that, the code is actually somewhere that it can be executed. So the JNI APIs provide us two different functions for this. First, we have system.loadLibrary, and this one is used if the SO file lives in the expected path. And that expected path within the APK is lib, and then a CPU keyword, which we'll talk about, /lib, which is lowercase, and then the name of the file, .so. So if you are going to and willing to adhere to that naming scheme, then you can use lib or load library. And you just need to use that little name. You don't have to put the full path. So for example, let's say it was libcalc.so. Then you could call system.loadLibrary on calc, with just calc in as the argument. And that then the underlying JNI will automatically detect which CPU you're running on. So whether you're running on ARM 64, ARM 32, which has a different keyboard, whether it's version 7 or not, whether it's x86, and previously Android also did support MIPS. So you as a developer don't have to make that distinction of which library to load at, or the Android app developer. If you use load library, it will automatically detect the CPU and select the appropriate library for you. Otherwise, if you are not going to put your native library under that lib CPU path, or don't want to name it lib and then the name, then you have to use system.load. And system.load requires the full path to the library that you'd like to load into memory. And so in this case, that means the developer has to manually select which CPU version of the library to load. So let's say you as a developer decide to compile your native code for ARM64 and ARM and x86. Prior to calling system, and you do not, for some reason, whether it's your malware developer want to hide them, whether you're downloading them dynamically from a resource and thus they can't be living in lib because they're not statically included within the APK. For whatever reason, you decide they're not going to be in lib CPU directory. So prior to calling system.load, you have to call functions that will detect whether you're running on ARM64, ARM32, x86, and then choose the select library and pass the full path. So when I say they're in different CPU directories, the keywords for the common CPUs that are supported is, first we have generic, quote unquote, it's actually what the documentation uses the term, 32-bit ARM, which would be ARMY-ABI as the keyword or the CPU directory. So you see lib ARMY-ABI libcalc.so. We have x86, 64-bit x86, ARM version 7, which is still 32-bit, or ARM64 is considered ARM64 version 8A is the keyword. So those are each of the CPU paths that are those default paths that we talked about that can be used with system.load library. So in this case, if those are all of the paths we have, all the libraries included in our APK, then we can call system.load library with just calc as our keyword, and it will automatically select which of those libraries to load. But now we've loaded it into native code, we've loaded our native code into memory by calling system.load or system.load library. But now how do we actually begin executing? Because currently all of our execution, as we talked about, is just in the lifestyle of the app, which is in Java code. So the first thing that you have to do as an app developer is declare the native methods in the Java bytecode. So we're saying, hey, here's the name of the function, here's the arguments it takes, here's its return value, and I'm going to tell the app that this is actually a native method, meaning it's implemented in native code or compiled C or C++, not within this Java or Dalvik executable. And so there's two options to then say, hey, this native method that I just declared told you the name and arguments of. Here's the actual function to execute when this is called. And so those two options for pairing are called dynamic linking or static linking. So dynamic linking works is that you use a specific naming scheme that allows JNI under the hood to say, hey, I see this Java declared native method with this name and these arguments, and I see this function in this native code library that we just loaded, and based on the names, I can automatically link the two and know that whenever the native method that's declared in Java is called from the Java, we're actually going to execute this function. However, that requires then in the native libraries to not strip symbols, which can make it much easier to reverse engineer what the functions are doing and how the library works, which both benign and malicious developers may choose that they don't want to do because they want to protect their IP. I mean, it's something that we talk about in the Linux space quite often that, most people should do strip all symbols or debugging symbols so that their functions have no names on them because that does make it much more difficult to reverse engineer and requires more investment of time and skill. And so if you want to do that for the native library that you're including in the Android application, then you would need to do static linking. Okay, just checking that we actually are recording as I'm still talking, because that would be quite the commitment. But so moving on. So static linking requires using the Java native interface API called register natives. And so register natives is going to, under the hood, do this linking. So let's talk more about these two pairing options. So first, dynamic linking, the resolving the native method names. So we're willing to name the function, or the app developer is willing to name the function in the native library so that JNI can automatically link it to the Java declared native method. So the name that it has to be in the native library or the .so file is it has first the prefix Java underscored, the mangled fully qualified class name underscore, the mangled method name underscore. And remember, in Java, you can overload methods. So you can have two methods with the same names as long as they take different arguments. And so in the case that this method name is actually overloaded, then we need to put two underscores and followed by the mangled argument signature. So we'll look at what an example of this looks like. But as you can imagine, this is a really strong signal as a reverse engineer because you don't accidentally end up with these very long function names. And so this is really helpful, and to make sure you use this if it's provided by the developer. Okay. So the static linking, on the other hand, is you don't have to name your functions. So, if you opened up an IDA, it would be like sub underscore address. But what you do have to do within the native library, not within the Java code, is called register natives. And register natives takes these different arguments, but the most important one for us as reverse engineers is the pointer to Java native methods. And so what's interesting about this struct is it takes it has three members. So first it will take the name of the Java declared method. So whatever that name you gave this method in the Java code, it will take that as a char star. Then it's going to take the signature of the method. A signature in Java is the types of its argument and the type of the return value. So we'll show an example of what that is. So again, that's a char star. And lastly, we have the address of the function where we should begin executing anytime that method is called in Java. And this address is within our native library. So that is how then we're going to pair the Java declared native method with the code to begin executing in our native library. And what's important about this is this requires plain text strings. Register natives has to have that plain text string name and the plain text string of the function signature to be able to execute and do a pairing. So if you are stuck, if you're trying to do this pairing of you've been analyzing an app and you run into the code is now calling into a native method and you need to figure out what it does, at some point you have to be able to find which function it is that's being executed within the native library, because JNI as a whole requires either the named function for Java or the dynamic linking, or it requires the plain text name and signature with the function address for register natives. So you will be able to figure it out. So what's a Java signature? Here are our primitive types, and basically what it says is, hey, we're just going to put together each of the different types that of arguments that a function takes along with the type of its return value. So this is the sort of code for each of the primitives, and then at the bottom here we see that if it's not one of the primitives, then we use L, and then the fully qualified class name, and then a semicolon. So what this looks like in practice is, let's say we have the function long, or f, which returns a long and takes an int, a string, and an int array. Then that means its signature, which would be passed as within the struct to register natives, is open parentheses to designate arguments. Int is a primitive and its code, as we see here, is a capital I. So we have I. String is not a primitive, so we're going to have L, and then the fully qualified class name, so Java lang string, semicolon, and then our last one is an int array. So we do an open square bracket to designate this as array, and it's of the primitive type I, and that's our last argument. So we close parentheses, and then we say we return the type long, and back in our list, long is J. So this is the signature for our function f, or our Java declared native method f. And so this, again, are really obvious types of strings that must exist in your native library if it's going to use register natives. Another example for function, or this is a full Java native method declaration as you would see it in the Java code. Public, the native keyword, its method name is G. It returns an object, and it takes a single argument, which is an object array. So our signature would look like open parentheses to designate the arguments, open square bracket to designate its array. It's an array of objects, so L, Java lang object, semicolon. That's the only argument, so close the parentheses, and then we return an object. So that's what a signature is. And now we're already ready to get into exercise number 5. So for exercise number 5, our goal is to not yet reverse engineer the assembly code, but we are going to practice identifying Java declared native methods in the DEX bytecode and then link it to the function that is actually executed within the native library. So to do this, what we need to do is define the declared native methods, figure out which libraries are loaded, because an app can include, and often does include, more than one type of native library. And so to understand which ones are loaded, you need to figure out which one your method or function is actually included in, so that you're not scrolling through all of them, maybe at 6 or 7, and instead really focusing where you think that function is implemented. Then we need to extract the native library from the APK, load that native library into a disassembler, so we are going to be using Ghidra, and then identify the address or the name of the function in the native library that is executed when the native method is called. And so in this exercise, we're using the sample mediacode.apk. So let's get to it. The first thing we need to do is determine, in our VM, we want to open up the app in JDEX. And the reason why we're starting with JDEX is, remember, we want to put ourselves into this sort of analyst or reverse engineer mindset. And if this wasn't an exercise, we wouldn't know off the bat that we need to look at the native library. We would likely start with the Java code and analyzing that and get to the point that we realize, oh, some of the code that we're interested in is actually implemented in native library. So just like we did in part 1, we're going to go ahead and start JDEX. Oops. Oh yeah, JNI GUI. So all of the samples should be in the home directory, and then samples, and we need mediacode.apk. So there's lots of stuff going on here. Clearly you would have started somewhere and ended up reverse engineering and coming to the point that you were interested in some native code. So one of my tips for finding native methods within a APK is that if you just search for the keyword lowercase native, you often will find a lot of variable names or function names that have native in it, and that's not quite getting to the declaration you're looking for. So instead, if you search for space native space, then that usually helps you find the actual declaration, because that's required in how in the Java code you declare that this method is actually a native method and implemented in the ELF or the native library. So we're going to do space native space. Oh, and I want to search for code. And we see 2 different native method declarations for this application. Oh yeah, so first things first, and I say this in some of the specific solution videos that aren't tied into the sort of like lecture part, is pause it and try things for yourself too. I'm going to keep talking because it would kind of be weird as I'm sitting here alone in my house to just sit and wait for an arbitrary period of time. So that is one of the pluses of recordings in this virtual, is pause, and I really encourage you to give things a shot yourself. And when you get stuck, then come back and then pause and then give it a shot, because I think that's really the best way that you figure it out and learn on your own. So I'm just going to continue though. So we have 2 different functions here. One in a highly jumbled, obfuscated-ish package or class name, and the other in what looks like potentially a third-party library. This is, bear with me, but we're going to go with the jumbled one because if, let's say, we were a malware analyst and that's why we began analyzing this application, then we're probably more interested in what this is than what this is. So let's start here. The other thing we should check out is, do we have native libraries included? So the way we would do that is coming over to this left-hand bar under Resources, and then we see here is our lib directory. And we see that they are using the default CPU path names. They have Army ABI v7, which is ARM37 version, or ARM32-bit version 7, Army ABI, which is quote-unquote generic, 32-bit ARM, MIPS, and x86. And under each of these, we see the same single library. So they've compiled one library for 4 different architectures. And so here's on the right-hand side, highlighted in yellow, our native method declaration. It looks very similar to a normal Java method, except it has this native keyword and there's no code. There's not the brackets in any sort of code, it's just a semicolon. And that is what our native method declaration is. And the rest of this exercise is to now figure out in the library what function is actually executed each time this is called. But let's hold on, because we want to make sure that we think this function is actually implemented in librrnad. And so what we can do is, yes, we see it down here, but you could also search for system.load library and system.load. And so we can be confident that this function or method is likely implemented in librrnad because in the same class, they're doing the load library. And yeah, however, let's go back to our search. And if we had focused on this function instead, we probably would have been a little disappointed, because if we scroll up and see call the system load library here, b equals bs patch, we see that they're loading a library that does not exist in this APK, and thus we wouldn't have found this native method bs patch within these libraries no matter how hard we looked, because it's likely in libbs patch, not in librrnad. And this is likely just dead code. They wouldn't be able to be dynamically downloading and to then load this library because they're using a load library rather than system.load. And so this library would have to live in these CPU directories, which it does not. So that's just something to keep in mind too, is just because they're doing something, like code can be dead and not executed or not work. So just something to keep in mind. So going back here, your next step is to extract the APK, unzip it, get the library you're looking for. If you're comfortable with ARM, then I would suggest just using Army ABI. If x86 is the assembly language you know, then go ahead and grab the x86 library. If you continue with Android reverse engineering, then I would suggest working on growing your familiarity with ARM, since that is what all Android devices run. But for this case and for this workshop, I wanted to more teach techniques rather than, if you know x86, you can learn ARM. There's no issues with that. So feel free to do whichever. Go ahead and pause this here and do those next steps. And once you've extracted the library, you will then open it up in Ghidra and work to figure out what function within that ELF or binary is executed every time this method is called. And the way that Java declare native methods or native functions are called is the exact same way as any other Java method. So we can click on this just like we did in part 1 and say, I had it. Got to click on it correctly. Find usage. And we see that they're calling it exactly, it looks just like a call to a regular Java method. However, in this case, the Java native interface would step in and execute the code that is in the native library rather than what is in Java. So you go ahead and pause, and I'm going to continue through the steps. So the first thing we're going to do, we're going to go to our samples directory, and I'm going to make a new directory for media code. Copy the sample into the directory. Then we're just going to unzip. Oops, I did not move into the directory. It's early, you know. I've had to change plans from the live stream to the recording. This is life, but it'll work just fine. So now if I ls on samples, you know, instead here's our lib directory. We'll need to move this before the next one. So if we go into lib, and I'm going to use generic arm, and then we have our librnad. So now we can start Ghidra, and I know that was exciting for a lot of y'all. So I've added it to the path so we can start Ghidra just by calling Ghidra run. And so Ghidra was released in April 2019 as a free disassembler and decompiler tool, and it is what we use for compiled code. Another tool that is commonly used in the industry is IDA or IDA Pro, but it is not free, and so that's why this workshop is using Ghidra. So we can close this tip. And the first thing we do is Ghidra runs on active projects. So unlike IDA, where IDA is file-based, Ghidra allows you to create projects that can have analysis of more than one file at a time. So we're just going to create a new project, and we're going to say a non-shared project. Ghidra allows you to set up sort of shared servers for collaboration if you're both going to, or more than one person wants to be analyzing the same binaries or set up files and working together. But in this case, we're not. We're just working on our own, so it's a non-shared project. I'm just going to keep the default, and we're going to call this Media Code 4 for exercise 4. And the next thing we do is we add a file, because we've created a project, but we haven't actually added the binary that we'd like to disassemble and analyze yet. So we're going to do file. Actually, that was not what I wanted to do. We're going to select that project just by, what am I doing? It's early. Okay, we're going to click the dragon. Yeah, because that's version tracking, and this is code browser. So we're going to first open the code browser. Okay, so this is where we can add the files. So we're going to go File, Import File, and then we're going to go to our samples and lib, since I did not move it into the media code directory, and I'm going to choose the ARM32-bit. So that's the directory I'm in, and we're going to do librnad, select file to import. and we're just using the default because it's an ELF. It has basically all the information about, you know, which architecture it is, that it's Little Endian, it's 32-bit, you know, things like that. So we can just accept the defaults that Ghidra detected based on the file format. And then, yes, we would like to analyze it. We're just going to use the defaults. Oops, here's the defaults. And so we've got a lot of windows here. And so this isn't intensive on Ghidra. There's a lot of great resources out there, so I would highly suggest you use those if this is a tool you want to get better. But for me, I also just use things. I do still use IDA for my day-to-day job because work provides me the license. Maybe that'll change soon. Maybe not. Who knows? But yeah, Ghidra's a really super powerful tool, and so if you're if I was just starting my career now, this was what I would focus on, build my tooling, my, you know, and everything for, rather than IDA. Except if you like IDA's graph view, and that's what you usually work in disassembly, I found that you don't like the format of Ghidra as much, but for the price difference, meh, I don't know. So, but anyways, so the first things we can do is, I'm sorry, I don't know how to change, I only have figured out how to change the fonts for the disassembly and the decompiler view, which are these two main windows. So those should hopefully be large enough, but I have not figured out how to change the font size on these left-hand windows. So hopefully they're large enough, but I will talk you through what I'm doing too. Okay, well, yeah. So in this middle window on the left-hand side, you'll see its name symbol tree, and the third one from the top is called functions. So that will show us the different functions we have here. And so remember, if a function is using dynamic linking to pair the Java declared native method with which function to run here, then we will see a very obvious name of Java underscore fully qualified class name underscore method name. And we don't see that here. We don't see any functions that begin with Java underscore. We can check again by typing here, and it finds nothing. So that means that this library is using static linking and register natives. We cannot just search for register natives here. It's an API call, but it is not just called from this. We do see two functions in this library called lowercase register natives. Those are things the developers did name, just so happen to. They are not the official API call to register natives. So I want for us to talk through this without just using that string, because that's just so happened that the developer did this. A lot of developers will not, because it gives things away. So I want to show you that process of how we would do it if they had not just chosen to give that information away by naming the function that. So if you do not have the dynamic linking of the class name and thus are doing the static name, then usually the things we can start to look for is there's going to have to be the string of the method, the name they use, and there's going to have to be the string of the signature of that Java declared native method, and those are passed to register natives. So if we can find those two things, then we can often find the call to register natives and thus the function, which is the third member of that structure. But let's talk through a few other things first within The other thing we will get to in the slides, but since it came up, is JNI onload, which is highlighted pink because it is an export of the library, is often where people will call register natives, because JNI onload, if it is exported from the library, it will automatically run whenever system.load or system.load library is run within the Java code. So since we saw system.load library was run, we can know that JNI onload was run at the same time. And so that is why usually it's a place where developers will put their call to the API call, register natives, in there, because then they know that after that point, that pairing will have already been done, and they can safely call any of their Java declared native methods without having to worry about ordering or when they'll call register natives. So that's one place to look. Another way to do this is to search for those strings we talked about. So we are going to do search program text. And so as we looked in JDEX, our method name is a single letter A. Any single letter string is usually very difficult to find within a database because it's a single byte followed by a 0 byte. And thus, that's hard for disassemblers or any tools to often determine that's a string versus another data type. So instead, I'm going to look instead for the string of the signature to see if that happens to be there. And so remember, our signature strings are going to tell us the type of the argument and the type that is returned. So in this case, because we always start with a open parentheses for the argument, and we have an L because our argument is of the type string. And so we're going to say L and then Java lang string semicolon close, and then we return void, and that's just the capital V. You do not need to have these memorized. I've done this exercise and taught this workshop quite a few times, as well as done a lot of reversing of Java native libraries, and so it just has invaded my namespace. And then we want all fields to search. And we can say it's case sensitive, so let's search all. I also could have just searched the strings, but, well, I forgot. So what we see here are places where in memory it's defined, and here in a function where it's being used. So let's go here as our first place. And so here we see in the disassembly view where they are accessing a string that matches our signature string. So they have L Java lang string. I personally don't love IDA's disassembly view, so I often change. I usually change the width of the function so we can see the full instruction, because here we are not seeing the whole thing. Where did it go? Okay, well, even after all that, which I cut out me trying to find the information. I still wasn't able to figure out how to get this to expand. But what I can show you is that if we right click on it and go to instruction info, we can see the whole instruction. So we're just going to go with that. And sorry about that, but we should figure out how. So what it is it would be store R3, which is pointing to our string, L Java length string V, our signature string, in the stack pointer +8, or otherwise known as local 10, since they try to give them a label or a name. And so what we would imagine then is if we are passing this ultimately and trying to build a struct, at some point we would see a struct where the string name is first, then comes our string of the signature, and then comes the pointer to our function that would be executed each time this Java declared native method of A is called. And so that is what the decompiler will show us as well. Is that if we bring this over, is that we're setting three things, three members, and then we're calling another function called register native methods. Try and keep in mind that, again, with these lower cases, that these are what the app developer named the functions, not what you can expect them to be called. But let's keep working. So even if we didn't see this, if we just saw that three things are being set, it would make sense to then double figure out, what is this first thing? Could it possibly be our method name or the function pointer? And so what's nice about Ghidra is if you click in the decompiler, it's going to highlight the same line in the instruction. So this is another great way to continue getting more familiar with assembly. So for example, when we click on this line again, it's going to highlight part of that line. Or maybe it doesn't always, but it does do the opposite direction. See, as that jumped. So what is this data at that address? So let's double click to take us there. What we see is there is an A that it did not identify as a string, but if we right click and we can say data string to say that this is a string, not that, now we have our function name. So far in memory we're putting, and if you remember, structs in C are represented as, sequential memory of its different members. So we have A, then we have our signature, which this would lead us to believe, if they are creating that Java native method struct, that this address, which is stored here at the next location, would be our function pointer. And so what we do, if we start at the beginning of this disassembly, to just walk y'all through it, so we're all on the same page as first. This is just the function prologue, because we're saving things off to the stack. And so then we're loading this address into R3. We're still in the prologue because then we are incrementing our stack to make space. And so then we're loading 1, 2, 3, 4 plus our program counter, which is usually how we get offsets in 16-bit ARM, or the 16-bit version of ARM, which is thumb. So we have, here is storing our string of A onto the stack first. Now we're getting the address for the string to our signature, and we're storing that onto the stack. Then we're getting the address of the function, aka our function pointer, and storing it onto the stack. And then we are loading the address for another argument that's going to be passed to register natives methods, again, the developers functions. And so what we see in the ARM calling conventions R0 is going to be argument 1, R1 is the second argument, R2 is the third argument, R3 is the fourth argument. And so we are taking whatever was R0 to register natives, which we'll talk about in the next section because it's going to be a default. That's going to be the first argument here, as you can see by param 1. And then we are going to use this native class for JNI argument. Again, these strings are all from the developer. Then we are going to take the pointer to local 14, which is the structure we just built here, and we're passing 1. Again, this is still the developer's function, so let's go to it and see what happened. So today really hasn't been my day in terms of technical difficulties, but we're back and we're going to keep working through it. So as I was saying, so now we want to see what does register native methods do? Because again, we can't just count on what a developer decided to name something. So we're going to go to this function. And what we can ultimately see, which we are about to talk about in the next set of slides, is that it here is going to be taking that struct of JNI native methods, which we passed in and constructed, which contained the native method name, the string of the signature, and the function pointer here to this function that we're calling as an offset of of parameter 1, param 3. So this is actually the call to register natives and the API function, and we will talk about why that is in a second. But that is why you cannot just search the code base for the register natives function name. But yeah, so now we know that yes, in fact, this structure that we just built is our JNI native methods struct, and thus, if we go back to that function, let's see where is register natives. If we go back there, then that means that this function pointer here, which we load in as the third member of our structure, which is the function pointer for the name. Oh yeah, I had to reload everything, so that's why this is back to being that. Data string. So this function native set app key is the code that we're actually executing whenever we call that method A in the Java code. And the reason why it has +1 here does not mean that we're actually going to start at 1 byte into this function. It's because we are operating and switching to thumb mode. So that is why the lowest bit is set, and if you're doing more ARM, you can see that, but we are in fact starting at the beginning of this function. So congratulations, you have done your first pairing between in JDEX whenever that native Java declared native method A is called. This is the code that is actually executed. So we did it. We made it through and did pairing using registered natives, but we still have some big questions about how did I know that that call to offset 35C was actually the register natives API call. And that has everything to do with this thing called the JNI environment, or ENV. And so that's the next big thing we need to know about in order to successfully reverse by native libraries that are included in Android apps. And because, as I had mentioned in part one of this, is my goal is to not teach basic reverse engineering, but to show you the things that you need to know about Android apps to do reverse engineering. And JNI Env is one of those things that is different than if you're just going to reverse a SO file that is for Linux. So overview. JNI Env is the structure of pointers to different JNI functions, so API calls. And every native subroutine or function in the ELF takes a pointer to the JNI Env struct as its first argument. And so we can sort of concisely put it from that JNI tips thing I linked. But the declarations for JNI End and Java VM are slightly different from C and C++, but the JNI.h file is what provides basically the listing of all the functions in the JNI End function. Normally, for the most common functions that are used from the JNI End pointer, I really haven't found impactful differences used in any apps I was personally reversing, but it's something to keep in mind of the ones that I'm going to provide to you here are the C definitions. So there may be slight differences for C++. So some of the most common functions that you may need to use within a native library that's in an Android app is, for example, register natives, which is at offset 35C in our JNI environment struct. So that is how we knew that that was a call to register natives. You don't have to memorize that. We'll get to showing. But for any of those APIs that are specific to when you're trying to use native code within a Java application, you're going to need certain functions that aren't usually necessary in pure C or C++ applications. Like, for example, you may need to find a Java class that's running within the process. Or instead of using normal C or C++ exception handling, you want to surface that within that Java application, and thus you may use throw instead. Or you might need to create new objects that once you return execution to the Java code, they can interact with. Or you may want to be able to call from your native code back into a Java method, and thus need a call ability to do that. And thus, as we've talked about, register natives is very important. So that's one of those things. So JNI Env is making these special API calls that native code that's running specifically with a Java application may need for these two languages to interact with each other. And so if we're using IDA, for example, we already saw what it looked like in Ghidra, but for IDA, what you'll often see is R5 here, because R0, the first argument to the function, is passed to R5. That's our JNI environment pointer. And then what we see is they first, where do they do it? They dereference it into R2, and then they add 2A4 to R3 and dereference that value to get the pointer. And then they do a branch and link to R3. So that's how they're calling a function that exists within that JNI environment struct. So there's a couple of ways to figure out, okay, what the heck is the function that's at 2A4? Because obviously, if I'm reversing, I want to know what functions it's calling. And so the first way is you can do it manually. So the way I did it was I created this Google Sheet by basically loading the JNI embed definition from the JNI.h file for C into a Trex. And then for each of the entries, it has an index and then an offset in decimal and an offset in hex. So for, 2A4 over here, if we then look for 2A4 as offset, we see that that's calling get string UTF-chars. So this call right here is to get string UTF-chars. This is not an efficient way to do that, so thankfully, we don't have to do this manually. but I always encourage people to understand how tools and plugins and things like that work. So if you do need to do it manually, or if you detect a bug in the plugin because something doesn't make sense, you can figure out the answer for yourself. So in IDA, if you have access to the hex-raised decompiler, not just the IDA disassembler, then in the decompiler, you can go to the first argument, because remember the JNI environment pointer is always the first argument to these JNI functions. And you can press Y to retype, add a new type to this, so we can change it from an int to a JNI end star. And once it's changed, then we see down here at B4 plus 676, which is the decimal value of 2A4, we see it changes it to get string UTF-chars. So that's how you can do that in IDA. If you only have the disassembler, then a wonderful intern who used to work for me named Io, she wrote this great IDA Python script, which will add comments to your IDA disassembly. So you can see which JNI function is being called. But since we're using in Ghidra, Ghidra also has a solution thanks to someone who goes by the GitHub username Aryx, or A-R-Y-X, I think that's Aryx. And so they provided a Ghidra data type file, and I linked to where they provided on their GitHub, but I've already loaded it in our VM we're using. But if, for example, it wasn't already loaded, you would go to the data type manager menu and open file archive, select the file, and then you should be able to retype any variable to JNI end star. And those directions are also with screenshots detailed in the Android app reverse engineering workshop for the text version on GitHub. And so as an example, this is what we can see. We've already seen an example, but we see, parameter 1 plus 18 is the function we're calling here. And once we do it to retype to JNI environment pointer, it's now find class instead of just plus offset 18. So that's the other just important thing to know. Instead of seeing all these indirect function calls, they're actually thanks to JNI environment pointer. And the other thing that's important to keep in mind too is if JNI environment pointer is always our first argument, that's not the first argument when we see it listed in the Java native method declaration. We actually have to scooch all of those arguments over 2 positions. So whatever looks like the first argument to the Java native method declaration is actually going to be the third argument in any of these JNI functions, because the first argument is always going to be this JNI environment pointer, and then the second argument is going to be the object that this function is being executed on. Because remember, Java is an object-oriented language. So if the function has been declared as static, which most native methods will, then that will just be null. But let's say you want to produce sort of a native function call on an object, then that object would have been passed in. But exercise 6, so we're finally going to put together all of the different pieces we've learned up until this point and reverse engineer an app that's implemented in native code. Yeah, I just said that. Cool. So we're going to go back to our definitions of premium SMS fraud that we talked about in part 1. So remember, to determine premium SMS fraud, we need to, 1, have an app that sends an SMS message. That SMS message needs to be sent to a premium number, and it needs to send to that premium number without user knowledge and or consent. So obviously, this code is probably going to be in the native code since, well, it's that's the exercise. But you can prepare, and you get out of this what you decide to put into it. So if you just follow along the answer, cool, fine. I'm not going to hunt you down because clearly you are your own human and you can do what you want. But you'll probably get more out of this if you go through the actions as if we did with exercise 1, and then figure out that the native code is what you want to reverse. I'm not going to necessarily go that path because I'm trying to get you all the answers, but yeah. And then we are going to need to identify the native methods and pair with their implementation in the native library. So we need to know what function is actually executed in the native library anytime the method you're interested in Java is called. And lastly, we need to reverse engineer that quote-unquote interesting native function to determine if it meets the bar for premium SMS fraud. So first things first, we're going to close this. And we are going to cd samples. The sample we're using here is HD wallpaper. I'm just going to remove that lib we unpacked and media code just because I'm having some issues with storage space. Because as I said, technical difficulties today. But I'm really trying, y'all, and I know y'all want the information, so hopefully, you know, don't let perfect be the enemy of good and all that. So first, we want to open up HD wallpaper in JDEX. Oops, did it again. JDEX-GUI. We're going to open up our sample. And you're going to use all those different skills we talked about first to figure out what code you're interested in. And, you know, maybe that's looking at launch points, maybe that's looking at strings and finding some you're interested in. But I'm going to skip ahead and just get us to the native method. Oh, well, I'm actually going to let it decompile first, it seems. Do, 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 do. Almost there. Oh, maybe. There we go. So I'm just going to do our little tip with space native, or I mean space native space. Oh, code. And we see this time lots of different functions listed here. And what's interesting though is they're all in the same class, so that can make it a little easier. So let's just choose the first one. And so they've named it JNI Manager, and we see all these different native methods declared, and they're calling System Load Library OC Helper. So let's check out resources, lib. They're using the default, that's why they can use load library. And again, we're going to do 32-bit quote-unquote generic ARM. And so here's our library. And so I'm just going to go ahead and open that up now. First, we have to file, new tab, unzip HD wallpaper. I'm going to remove everything about besides the lib, because as I told you, space issues and want this to go smoothly. Okay, so if we go cd into lib, then we see our different CPUs, and there's liboc helper. So now I'm going to start Ghidra. So this just reopened librnad, so I'm actually going to click and we're just going to close it, and we can just import a new file since for this case it doesn't matter all that much since we're just doing some tests and analyzing it. But if you were starting a new project, you would probably create a new project rather than combine them. But yes, we want to analyze it using default again. I forgot to show y'all last time around, but a strings window, which is always important. So the way you open that is go to in the top bar of window, and then you can come down to define strings. And so here we have all of our strings. So we can usually, if we had a reason to believe, this native library includes code that potentially is doing SMS fraud, then we can, start doing things like look for SMS. And so some of the interesting things that come up is we see Android telephony SNS manager, and different things like that. So that might be an interesting place to start. We could scroll up and see which function this is in. So it's in one of our native methods. Let's go back to the deep compile string. And so in this case, they're using dynamic linking because here we have that naming scheme that we talked about, and it's really obvious. So it's Java underscore the fully mangled class name, so com.mbva SDK library manager JNI manager underscore, and then the method name. And so what that would match is com.mbv.a.sdk library.manager.jni manager, and then the function name, which was native send. So y'all, this is just one way to go about it. I've clearly done this exercise many, many times as I've taught this workshop. So looking for SMS is one different way. You could have started in JDEX of looking through the different places each of these are called, and end up here. Like, that's where reverse engineering is part science, and sometimes a lot of luck of just having to search for the right things, and your luck gets better the more work you put in and the more you do. But so this function clearly is pretty interesting because we go ahead and see some strings like send text message, which we talked about is one of the ways to send a text message. So let's go ahead and start here. So we have this int, and we see some different JNI environment pointers here. And we see the string send text message, but are they actually calling it? What are they doing? So the first thing we can do is, as we talked about, this is going to be our JNI environment pointer because it's always the first argument to any of these JNI methods. So let's retype this. We can right click, and do retype variable, which the hotkey is also Control L. And then we're going to do, I don't have it loaded here. So actually the first thing we have to do is in this bottom left corner window, it's our data type manager window, and we need to import JNI all. So we are going to go to, where is it? Where is open archive file? Menu, sorry, the little drop down thing, and we're going to say open file archive. And then in the home directory, we'll see jniall.gdt, which is what I downloaded from Eric's baby, GitHub that they so kindly provided to us. And so now we see JNIall here. So now we should be able to retype. So now come back here, retype variable, and we're just going to retype it from an int star to JNI capitalization managers env pointer. And so it's the second option that showed up. And so now we see that this is actually, we can see the different functions listed here rather than just seeing, these BLXs to a offset from the first argument. So this is where the decompiler can definitely be helpful for understanding what is happening, but again, always, verify your understanding based on the disassembly. So what we can see is the first thing this is doing is trying to find a class so that the native code needs to interact with a class object that exists in, sort of the Java world. So we're going to find the SMS manager class. And this is where, until you get fully familiar with all of the most common of the APIs, what we can do is open up that link that I provided under resources for JNI functions so we can double check the specs and understand what it takes as arguments and what it does. And so if we look for find class, oops, I thought this was the one that gives us, here it is. So it's going to take the environment as its first variable and then the class name that it wants to find and returns the JClass object for that. And then we're going to call getStatic method ID as long as the class is not null. And so we want to get the static method ID for the method getDefault. Because if you remember in Java, in order to call sendTextMessage within the SMS Manager class, first we need an SMS Manager object to call sendTextMessage on. So that's what this is doing. So we can look back here and say get static method ID, and it returns the method ID for a static method of the class. Purists will not like me making this comparison, but I think it made sense to me as I was learning this, is that the way that we call these Java methods from the native code is very similar to sort of reflection, and that you need to find the class, find the method ID, find the object, and then you can sort of call invoke. But in this case, instead of using invoke, we do call and the return type of the method. So call, you might see it like pointy brackets and then method for whatever type that method is. So we get the method ID, and then we're going to call that method. So in this case, we're calling static object method of getDefault from pvar1, which is passed here. And so now we have the result of calling getDefault. So this pvar2 is now our SMS Manager object. And then we need to get another method ID. So this time we're getting the method ID for sendTextMessage. And here's that long signature for sendTextMessage. And pvar1 is now that method ID for sendTextMessage, and ultimately we're doing call void method. So first parameter is JNI Environment, second parameter is the object we're calling it on, because remember, Java is an object-oriented language, so that's our SMS Manager object. Third is now the method ID we want to call, which is sendTextMessage, and then we pass in all the arguments to sendTextMessage. So that's going to be param3, 0, param4. Going back, we need to remember what are the arguments to send text message, and we talked about this in exercise 1. So what we care about is where are we sending this text message to? And the first argument to send text message is always the mobile number. So that means the third argument to native send is that mobile number that we're sending the text message to. So here's the destination number. Going back to disassembly, just because I feel like I'm setting all up poorly if we don't make some connections. So coming down to call void method, which remember previously just looked like an offset from parameter 1 before we set this as a JNI environment pointer, is that let's look at what is passed in here. And so IDA doesn't do this where it's going to sort of rename all your params here for it. You'll just see the different registers like R0, R1, R2. Whereas instead here, they're renaming them to basically different names. I personally prefer to see, the registers and don't like the quote-unquote help, but, to each, and this is a different thing you can turn off each time. Yeah, so actually now that I remember that, it doesn't, we're not going to talk through the calling convention of R0, R1, R2. For ARM, it doesn't make as much sense to go through the disassembly, but basically, yeah. Okay, so the next thing we have to answer is we can see that if this native send is called, then it will send a text message. But who would it send it to, and does it ever call? And so in this case, we need to return back to our Java code to answer that question, because the Java code is what is ultimately going to call native send and also pass in this argument. So remember, whatever arguments are in our Java declared native method are scooted over 2 positions in the native method subroutine. So this argument number 3, which is the number we're sending the text message to, is actually going to appear as the first argument in the Java code, because JNI Environment Pointer takes the first position, and then the object that this function would be performed on takes the second. So let's go back to JDEX. So here is native send. So this argument right here, str, that's that native, or that's the destination number that we're sending the text message to. So if we go to find usage, we see one place this is called. And so in this function, whenever it makes it to this point and calls the message, that is that native code being executed. Stir is passed as the first argument here, so we can continue going backwards. And what we would find is it's that function, just right there, with these 2 different arguments, is that we're passing a short code in as the first argument based on their naming, and a keyword, which would end up being the body of the text message here. And so if we look at this get empty shortcode function, we're going to return whatever value they've set as the shortcode for this data. And I mean, depending on, art science, this might be good enough for you. We'll follow it a little further, but it's similar to the same thing we did in exercise 1. So again, we can find usage of where they set this shortcode. There's 2 different places. So let's just choose one of them. And what we would find if we continued to follow this back using the skills we gained for Java code reverse engineering in part 1 is that they're receiving this again from a remote server. And so we can be pretty confident that that short code is a premium number based on its name too. And then we also want to figure out how are they calling. Does there include user consent in this control path? So again, we'll do find usage. So they're calling it here. They're checking that they had gotten the code data. This is part of that path. And there's a couple different places. The reason why all of these are single lowercase letters is because they are using a common obfuscator, and which just renames everything as lowercase letters. So here they're creating a separate asynchronous thread, which is going to run that code. So we can continue to follow this back. Which they start at different times. This is not very interesting. But ultimately, if you follow all of this back, what you'll find is that went recursively, chose the wrong. Okay, so since I want to get this up for y'all, also you can check out on my channel, I have the full solution as exercise 6 separate video. But yeah, so that is how you figure out by combining skills in reverse engineering native binary code with Java code. That's the connection between the two, and that's the goal of this workshop is if you have done a lot of binary reverse engineering and am comfortable reverse engineering those separate elves, now how do you apply those skills to Android apps? And if you're in an Android app and looking at the Java, and you see that suddenly code, it's calling into a native method, how do you find that code? And so hopefully those are the skills that you're taking from this. And again, I really appreciate you hanging with me through all these technical difficulties. Hopefully you understand that I'm just trying to put this out there into the universe for free for anyone who can use it, and I'm not any sort of professional streamer or video maker, but hopefully even if these videos aren't perfect, sometimes there are major technical difficulties that it helps. And also remember, if the video is not your favorite, that I've also put all the information through text writing online as well. So thanks for hanging in there. I always appreciate and I'm honored when you use some of your time to go through this, and we could always use more people helping to protect users of Android. Yeah, so thank you. Let me know what you think, I guess, or not. Okay, I'm just going to end this now. Bye.